Okay, well, thanks very much for tuning into this. Thanks especially to the Philosophical Society for asking me to give this talk. It's an honour for a philosopher to be giving a talk to the Philosophical Society. So let me begin by trying to explain what I'm going to do in this talk. It's divided into three sections. First of all, I'm going to try just to briefly explain how I'm using this term Universal Darwinism, and also why I think it's relevant to talk about it now, nearly 40 years after the publication of the paper that initially used the term. In section 2, I'm just briefly going to give an intuitive sketch of why I think the position of Universal Darwinism is appealing to people, why I think it grips people and strikes them as intuitively right. But then in section 3, I'm going to try and look in detail at exactly what we mean by Universal Darwinism, subject it to more focused scrutiny and tease out some specific themes to look at. And in the end, I'm going to conclude by saying that there is a form of Universal Darwinism that survives scrutiny, but it turns out to be a much weaker, much more watered down position than we might initially have thought. And I think that's important for the purposes of evolutionary explanation as well. And before I move on, I should also say that all mistakes in this talk are of course mine, but the insights I have are due in large part to really useful conversations I've had with Richard Watson, a friend and colleague at Southampton, and also to work by Azita Chelapu, formerly graduate student with us in the History and Philosophy of Science department in Cambridge, now working at Bochum in Germany. So thanks to both of them. Okay, so first section, what is this Universal Darwinism position? Why do I want to discuss it now in 2021? The phrase Universal Darwinism, as far as I've been able to tell, first traces back to this paper by Richard Dawkins from 1983. So not quite 40 years on, but nearly 40 years on, and probably by the time this underlying written paper has been through the usual iterations, it probably will be 2023, so 40 years on by then. This paper of Dawkins is I think a very rich one, a very closely argued one, and in that paper he tries to do a few things. Universal Darwinism, as he uses that phrase, is introduced actually in the context of what was then a kind of fairly early program of astrobiology, the study of life on other planets. And Dawkins was interested to claim, as we see here, that Darwin's theory of evolution is more, he said, than a local theory to account for the existence and form of life on Earth. It's probably the only theory that can adequately account for the phenomena that we associate with life. So by calling Darwinism universal, part of what Dawkins was getting at in this paper was that actually the theory of Darwinian evolution is a theory that he thought won't just apply to evolution on Earth. Anywhere that you might find life in the universe, you will need to use a Darwinian framework to understand it. That's a fairly ambitious claim, but if anything, Dawkins grounded it and justified it by appeal to a claim that was even more ambitious. Dawkins said that the reason why we can be confident that anywhere we go in the universe will always need to appeal to evolution by natural selection is because, as he puts it, only Darwinian explanation is in principle capable of doing the job of explaining the existence of adaptive complexity. Anytime you see adaptation, anytime you see the suitable organisation of means towards some valuable functional goal, you can be sure that Darwinian selection lies in the background. And that's not just because it happens to be the correct theory of adaptation as we find it, it's because it's the only possible theory that could make sense, even in principle, of these phenomena of adaptation. And this is the claim, this second claim, this claim about the necessity of appeal to selection in the explanation of adaptation is going to be the focus of scrutiny in this talk. So now you know roughly what Universal Darwinism is. We'll say a bit more about it later. Why talk about it now? Well, for the past decade or so, there have been, I think, ongoing ways in which this Universal Darwinism debate has resurfaced in recent biological thought. So just to give two examples, and I think we could give more, but just to give two examples, the truth or the plausibility of Universal Darwinism was, I think, very much at stake in a fairly recent and ongoing debates over the so-called extended evolutionary synthesis, the idea that perhaps we need to fundamentally rethink evolutionary theory. And Universal Darwinism, the relation between selection and adaptation, is also very much at work in the context of ongoing theorizing and empirical work again on cultural evolution, on the idea that we might think of cultural change as akin to an evolutionary process. So let me just say a tiny bit more about these. The extended evolutionary synthesis is a very diverse program in which theorists, mainly in the biological sciences, but also in philosophy, have argued for a whole series of what they see as necessary revisions and extensions of mainstream evolutionary thought. They focused on many, many different themes relating to, among other things, the most important mechanisms of selection, the most important mechanisms of inheritance, I should say, the relationship between organism and environment, but they've also focused on this key issue around the relationship between selection and adaptation. And so you find those who have argued in favour of the extended evolutionary synthesis, so you'll see here at the top a picture of Kevin Leyland, but there are many others, that they've argued, as they put it, the burden of creativity in evolution, i.e. the generation of adaptation, does not rest on selection alone. On the face of things, in outright contradiction of Dawkins' claim. And then you find many biological theorists responding very vigorously to this, often eliciting very Dawkinsian-sounding claims. So here's Doug Fatuma saying in indirect response that in his view, directional or positive natural selection is the only known cause of adaptive change. So you see this dispute surfacing very, very clearly in recent thought. You also see it, I think, in recent discussion around cultural evolution, and I'm using this term cultural evolution in a fairly loose way here, but suffice to say that many theorists, and this is present in the work, particularly people like Richardson and Boyd, but also in important work by people like Alex Massoudi, Joseph Henrich, and here Celia Hayes, that they've all said that in some way or another in the human species, but in other species too, change in those species is not simply a matter of traditional evolutionary forces acting on genetically inherited variation. There are also, they say, ways in which species are moulded, species change, species respond, in ways that are underpinned by how individual members of those species learn from each other. Very clear case can be made for the importance of cultural evolution in humans, but humans are not the only social species. Obviously, they're not the only species whose members are capable of learning from other species members. Now, what we see in the cultural evolution literature is a sort of meeting ground where there are important synergies between those who, on the one hand, propose Universal Darwinism, the explanatory monopoly of selection on adaptation, and those who propose forms of evolutionary extension. One thing that the extenders have been keen to suggest is that there are many inheritance mechanisms, they claim, other than genetic inheritance. And so it's possible for the Universal Darwinist to endorse some of the themes of evolutionary extension by saying, yes, maybe selection really is the only process that can explain adaptation. But so long as selection can occur in many different substrates with many different underlying mechanisms of inheritance, we can maybe have alternative forms of natural selection producing adaptation, but not based on genetic variation, based, for example, on cultural variation instead. And so you find Kevin Leyland actually again endorsing this line of thought, this time in a very nice article with Alex Massoudi, where Leyland says cultural evolution itself is a Darwinian process, comprising the selective retention of favourable culturally transmitted variants. And they will appeal to this form of selection as a way of explaining adaptation in culture. Celia Hayes, in this wonderful, fairly recent book, Cognitive Gadgets, in some ways takes a slightly different angle on this underlying cultural evolutionary idea, claiming that in fact we should see the human mind not simply, and in some ways even not primarily, as a product of selection acting on underlying genetic variation, but we should see the mind itself as a product of a form of cultural selection. As she puts it, the designer of the human mind is natural selection acting on cultural rather than genetic variation. So still an appeal to a Darwinian selectionist explanation of adaptation, but not using genetic inheritance. And of course this was also an idea that Dawkins himself was very fond of. Just to allay historical worries, although I've said that I'm giving a roughly 40-year age to Universal Darwinism, that's just because Dawkins' own use of the term Universal Darwinism is approaching 40 years old. The underlying idea that Darwinian processes, that selection processes, might be at work outside the strict organic realm is very old, much older than Dawkins' paper. In fact, it's pretty much as old as Darwinian thinking itself, even as Darwin's own thinking. So Darwin himself, in The Descent of Man, tells us that in his view, as he puts it, a struggle for life is constantly going on amongst the words and grammatical forms in each language. The better, the shorter, the easier forms are constantly gaining the upper hand, and they owe their success to their own inherent value. And Darwin adds that, in his view, this is a form of natural selection, albeit not selection acting on the usual kind of organic variation. And perhaps best known for proposing the necessity, the obligatory nature of a broadly Darwinian process in explaining adaptation is the man whose photograph we see on the right of the slide here, Donald Campbell. As he put it, a blind variation and selective retention process is fundamental to all inductive achievements, all genuine increases of knowledge, all increases in fit of systems to their environment. And this was Campbell writing in the 1970s. Okay, so I've said a little bit to put Universal Darwinism in context and explain why I think it's still worth addressing, or why it seems like a current topic of interest. In this second part, which will be very, very brief, I'm just going to say a little bit about one might feel that Dawkins has to be right, that ultimately adaptation has to be explained by appeal to natural selection, and nothing else could possibly do the job. You get a hint of this kind of argument, right back as far as Darwin himself. So this is a passage right from the very beginning of Darwin's Origin of Species, where he's pointing out that many theorists before him had suggested that the species that we see around us owe their commonalities in form to the fact of descent from common ancestors. That idea of evolution was not new to Darwin. But Darwin says, at the same time, though, we've got to explain how adaptation occurs. And merely pointing to common descent by itself doesn't seem able to do that. And yet, surely adaptation has to receive some kind of explanation, because it's simply too much to say out of the blue, perhaps this wonderful adaptation simply arose from nothing. perhaps through some just great cosmic chance. So here he's talking about the then very popular book Vestiges of Creation, which had also proposed a broadly evolutionary view, asserting common descent. And Darwin says, the author of the Vestiges of Creation would, I presume, say that after a certain unknown number of generations, some bird had given birth to a woodpecker and some plant to the mistletoe, and that these had been produced perfect as we now see them. But this assumption seems to me to be no explanation, for it leaves the case of the co-adaptations of organic beings to each other and to their physical conditions of life untouched and unexplained. Some kind of explanation is surely required. And how on earth are we going to produce that kind of explanation? What kind of constraints can we set? So when we're talking about adaptation, in broad terms, we're talking about the existence of structures that show a not necessarily perfectly functional arrangement, but just a moderately functional arrangement of matter. And a moderately functional arrangement of matter is unlikely to appear whole and well-formed, well-configured, all at once, just by chance. And so we might think, on the one hand, we need some kind of sorting process, some kind of discriminatory process that can pick better adapted arrangements when they arise. Pick them and keep them for further refinement. And we also need some kind of what you might think of as productive process, something that is able to throw up a range of different configurations, introduce variation into those somewhat well-suited variants that we happen to have retained from previous rounds of sorting. And you might further add to this that the productive process in question can't be rigged so that we simply stipulate that it already has miraculous abilities that enable it to produce the right variants, because that's just as miraculous as a well-adapted form of matter coming into existence by chance. And so put those things together, it looks as though it's part of the adequacy conditions on an explanation of adaptation itself that a selection process has to be involved. And that, I think, is one of the big reasons why Universal Darwinism seemed so appealing to so many. Okay, but now I want to move on and try to scrutinise Universal Darwinism in a little bit more detail, because all we've really done so far is give a loose and I think intuitive justification for why the Universal Darwinism position seems compelling. And then this third and final section, I'm going to try and subject Universal Darwinism to a bit more scrutiny. So the key claim here that we're going to be looking at is Dawkins' suggestion that only Darwinian selection, no other process, is in principle capable of doing the job of explaining the existence of adaptive complexity. In what follows, I'm going to suggest that we can give 4 slightly different readings of that claim. We might be saying that all explanatory questions relating to adaptation, regardless of what kind of question they are, need to be answered by appealing to selection. We might say, well, no, it's just that all explanatory questions relating to what we might think of as the design quality of adaptation need to be answered by appeal to selection. We might instead think that the key focal claim is something like this: the past history of selection is what does the explanatory work in explaining adaptive features of variation itself. Or fourth, we might think that the focal claim is that whenever you find an instance of adaptation, it's always the outcome of a selection process. Now, you might think those are all the same claim. You might think I've just said the same thing 4 times over. I'll try to convince you, first of all, that these 4 claims are all actually slightly different, that they're importantly different. And I'm also going to try to persuade you that none of them is plausible. None of them is quite right. So here goes. So that's going to turn out, I think, to be fairly bad news for Universal Darwinism. Okay, so take 1. We might say, here's what Universal Darwinism says. It says that all explanatory questions, regardless of what they are, that we might ask about adaptation need to be answered by appealing to selection. Well, philosophers might say, hang on a minute, explanation is typically contrastive. And depending on which contrast you pick, different answers are appropriate. So just so you see what I mean by that, you might ask, why was the Olympics postponed in 2020 rather than in 2012? To which the answer is something like, well, there was a pandemic on in 2020, but not in 2012. Introduce a different contrast, a different rather than, and a different answer becomes appropriate. Why was the Olympics postponed in 2020 rather than cancelled? Well, there the answer presumably has something to do with the importance of the event, maybe the amount of investment and training that had already gone in, and a desire to ensure that it didn't disappear from Tokyo altogether. Different contrast, different appropriate answer. I think this is worth bearing in mind when we ask whether it's really true that all explanatory questions about adaptation need to be answered by appeal to selection. Often they do. So if we ask, why is it that we see adaptation X in a particular species rather than an alternative, less fit trait such as Y or Z? And the answer might well be because selection favoured X over those alternatives. X made the species in question fitter than those alternative traits. So selection often is the right answer. But it needn't always be. We might instead ask, why do we see adaptation X rather than equally fit traits, Y and Z? Well, there, if Y and Z really are equally fit, or maybe they're even fitter, then selection's not going to be the right answer. Instead, the answer might be, there were constraints on the developmental system that made variation in the direction of X more readily available than variation in the direction of Y or Z. Y and Z simply weren't biologically possible or were not likely given the developmental system of the species in question. And folk working on developmental bias are very used to this type of, on the face of things, non-selective explanation. Now note though that we're maybe not asking about adaptive fit here. We're simply saying YX rather than some different traits, Y and Z, that maybe could have arisen but didn't. And so you might have a second kind of approach to this. You might say, look, maybe as long as our questions are about the design quality of adaptation, as long as we're trying to explain why it is that these traits in question are so uncannily well suited to their roles, then we really do need to appeal to selection. But even this, I think, is something that in recent years we've seen good reason to doubt. So a nice paper by Tobias Uller and colleagues, including Paul Brakefield, recently retired here from Cambridge, and also Leyland and some others who have been involved in the extended evolutionary synthesis movement. They published a paper just quite recently arguing that developmental bias can also play a role in facilitating adaptive evolution. Roughly speaking, developmental systems can be set up such that they have a tendency to produce suitable variation in the right direction, or at least variation biased in that direction compared with what we might expect if instead variation were completely random with respect to fitness. Rather than necessarily going into detail about how exactly they make their case, I think we can also think of actually much older work from people like Richard Lewontin. So a photo of Lewontin there on the top right of the slide. Lewontin argued way back in the 70s for various ways in which developmental processes are themselves important in explaining the design quality of adaptation. So Lewontin pointed out that if development was too tightly integrated in an organism, then that would tend to mean that any beneficial variation in one direction would tend to bring with it all kinds of knock-on effects throughout the organism, which by and large would tend to be negative. And so even though you might get some slight payoff with regard to some aspect of fitness, it would be messed up by tight developmental integration, bringing about counteracting overwhelming negative effects on fitness elsewhere throughout the organism. And so Lewens argued for the importance of a certain kind of developmental modularity, a certain kind of, as he put it, quasi-independence, that could allow some traits to vary independently from others. And that crucially, this would be really important in helping to explain how well-designed creatures could come to evolve at all. And so here again, we see the appeal to developmental processes rather than selection in the explanation of adaptation. Now, you might point out here, okay, sure, maybe sometimes developmental processes do play a role in explaining what we might think of as design quality here. But how come those developmental processes get to have the right kind of configuration? How come they tend to produce, appropriate forms of adaptation, for example? Surely that itself needs to be explained by appeal to past rounds of selection. And curiously enough, that's also what people like Uller and colleagues are arguing in the paper that you can see on the slide here. Now, what that means is at this point, you can get the sense that there's a kind of talking past each other almost. So everybody agrees that, yeah, there are some questions about adaptation that you can answer by appeal to things like developmental bias. But it also turns out that those very people think that, sure, natural selection itself may well be there somewhere in the background when we want to explain why it is that those developmental biases are indeed suitably tuned. So even those people who argue sometimes for the importance of phenomena other than selection in explaining adaptation often don't deny that selection might nonetheless be at work somewhere in the background. Now, at this point, I think we come on to the third and fourth ways of cashing out what the content of Universal Darwinism might be. And I think these become really quite interesting, and we begin to see where there are genuine disagreements between different factions. So I've just said that even some of those evolutionary extenders are perfectly willing to make room for the idea that often it's the past history of selection itself that explains why it is that variation, why it is that developmental bias has these adaptive features. But is it true that that past history of selection is always what explains adaptive features of variation? So here I think we can get some nice insights from work on machine learning in connectionist systems. So we're going to have a little bit of a digression here to talk a little bit about learning in these connectionist networks. So Nick Shea points out that one of the remarkable features of connectionist networks, these kind of neural networks that many people are now familiar with, is that they can often correctly classify new samples which differ in their input from anything encountered during training. That's what makes them useful, and that's why people want to use machine learning for all kinds of things, from play and go to diagnosing disease. And sometimes when they work as one wants them to, these networks are able to avoid problems known as the problem of overfitting and the problem of underfitting. And I'll say a little bit about what those mean in just a moment. So here's a quick digression to explain some basic features of these systems. So the goal of these kind of learning networks is that we're usually trying to build systems that you can expose to a limited set of inputs, which we call the training data. And after exposure to the training data, they can then give appropriate responses in the context of new inputs called, and I've written here the training data, but that shouldn't, that's, we actually want to think of those as new samples there. So sorry for that typo. So we begin by feeding our system images of maybe dogs and cats, if we're trying to build a system that can discriminate between dogs and cats. So maybe we give the system these three pictures here. So we've got Roscoe's dog, Flash, Here's Tricky Woo from the original All Creatures Great and Small series, and here's Schnorbitz with Bernie Winters. I thought I'd pick dogs from the 80s since we're talking about Dawkins's Universal Darwinism paper from around the same era. So we might feed this the training set to this system, and we'll need to feed it various images of cats as well. And then the question is, when we give it a new input, not in the training set, will the system be able to recognise my in-law's dog, Bryn? Here he is. And Bryn is a dog, but doesn't look all that much like those other dogs. And it might be not. That system might have learned in such a way that it associates dogs in the training set with maybe incidental features of the background. So how those dogs are held, maybe overly specific features of their anatomy and so forth. This is the problem of so-called overfitting. Roughly speaking, the idea that these networks might learn too much from the training set, which means that they can't generalize appropriately. More rarely, there's a problem of underfitting, usually when the system hasn't been exposed to the training data for long enough. And if overfitting is learning too much from the training set, underfitting is not learning enough. But sometimes these systems do acquire a good capacity to generalize. It's not a given that they do. It's certainly not guaranteed that they do. They won't always. But when they do, that's a valuable thing. And when they do, there's no miracle associated with that. Is there something similar? Is there something similar in the context of natural selection? Well, yes, there is, although biologists don't usually talk about things in this way. Systems that adapt by natural selection also face a risk of overfitting in pretty much the same sense. Here's a peppered moth, well camouflaged against a lichen-covered tree. A population of peppered moths might well end up adapting to overly idiosyncratic features of the visual systems of the specific birds that happen to be in its locale. Roughly speaking, the moths might learn too much in that sense about very idiosyncratic features of their environment. And if that happens, then in fact they'll be less well adapted in the event that different birds without those visual idiosyncrasies happen to arise in the environment. And usually, of course, evolved systems avoid this problem of overfitting. But in principle, it's there. In principle, selection could lead to overfitting. And in a manner that's linked to this, Alfredo Rago and colleagues have pointed out that selection, when it works too well, when it works too efficiently, rather than producing better adaptation, can in fact be the enemy of adaptation. And so if it's selection working too well that's explaining adaptation, that's the enemy of adaptation, we need to explain good adaptation by appeal, not to selection, but to selection's own inefficiency. So Rago and colleagues say adaptive plasticity in coarse-grained environments, in other words, the ability to respond to a certain amount of environmental change, evolves as a byproduct of inefficient short-term selection. When selection's too efficient, plasticity is lost and the system does not do well. Populations that rapidly evolve their phenotypes in response to selective pressures follow short-term optima, with the result that they have reduced long-term fitness across environments. So we already see selection is not what's doing the work here in explaining quality of adaptation. Richard Watson here, in collaboration with Urs Staffmery and also with other colleagues of his in Southampton as well, has stressed in extremely interesting ways the very close analogies that we can draw between learning in connectionist networks and evolution of organic populations. So they point out that there really is a sense in which evolution can have foresight. And this seems, I think, shocking to many people who are used to the Darwinian notion that the whole point of evolution by natural selection is that it's blind. But I think once you've seen the twin risks of overfitting and underfitting, you also begin to see it a lot better, what Watson and Thackeray have in mind. So neural networks, connectionist networks, do have foresight, just in the banal sense that they sometimes end up with the ability to generalize well. Not always, but sometimes they do. To generalize to unseen data beyond the training set. And in a sense, evolution is doing the same thing in the context of natural populations. And as they put it, the possibility that evolution can learn from experience to favourably bias future exploration need not be any more mysterious than the basic result that learning from a training set can produce good generalisation on an unseen test set. So we've seen that the ability of neural networks to generalise beyond the training set is a genuine phenomenon. It's something that these networks can do, that they're not simply reliant on rehearsing diagnoses of the training set itself. They can sometimes correctly get Brin right, as well as those other dogs that we saw on the slide earlier. It's not a miracle, but it's also not inevitable. Not every system does this. And as Watson says, evolving systems can do the same thing. And it's useful to reflect on how we explain these abilities to generalize this form of foresight in the context of neural networks. So Nick Shea, again focusing on neural networks rather than on evolving populations, points out that we need to explain why it is that networks have this ability to generalize well at all. And he says, look, at least part of that story is ahistorical. It's an account of how, after learning's finished, the network nonetheless is able to correctly classify a new sample. And as he puts it, this isn't an explanation in terms of facts about the network's developmental history. It's not an explanation that relies solely on exposure to the training set. In order to explain the ability of the network to generalize, you need to appeal to non-historical facts about its actual internal structure and the dispositions of those structures in relation to features of the network's environment. So we explain a valuable ability of this system, not in terms of the history of the system's exposure to samples. Analogously, when you explain the adaptive abilities of organic systems, sure, part of the story is in terms of the exposure under selection to environmental pressures. But part of that ability, part of that explanation also has to appeal to the internal structure of the evolving systems themselves. Okay, take 4. Is it true that all instances of adaptation are the outcomes of selection processes? Now, so far I haven't said anything to deny this. I haven't said anything to deny that maybe every adaptation you see is indeed a product of selection. All I've said is not all the explanatory questions that you should be asking about those processes necessarily need to relate to selection. And this is the sort of thing that Dawkins was worried about. So, as he puts it, hard grains made of quartz or diamond. He's thinking about differential erosion here. Hard grains made of quartz or diamond will last longer than soft grains made of chalk. He's imagining the elements wearing away at a body of rock. But nobody's ever invoked hardness selection among sand grains as the basis for an evolutionary progression. The reason, he says fundamentally, is that grains of sand do not multiply. One grain may survive a long time, but it does not multiply and make copies of itself. And so what Dawkins seems to be suggesting here is that maybe one reason why selection really is necessary for adaptation is because reproduction is necessary for adaptation, and selection is the kind of process that involves reproduction. So is it really true that reproduction is always required for adaptation. This kind of multiplication, this kind of making copies. No, it seems to me. So go back briefly to what we said about neural networks. In a neural network, and here you see kind of simple schematic illustration of a neural network on the right. The configuration of the system changes over time, for sure, and absolutely essential that the configuration of the system changes over time. Particularly what changes are the weightings of connections between the nodes in the system. And often, at least, those weightings are changed in a manner informed by calculation of error with respect to the desired output. So those weightings will change over time with repeated exposures to our training set. And the system adapts, the system gets better, the system maybe produces something very valuable in terms of classificatory abilities over time because of those modifications. But is there any reproduction going on here? Is there any multiplication going on here in the production of adaptation? It seems to me no. Maybe sometimes learning might work in this way. Sometimes learning might work with reproduction, but a single neural network can just persist. It doesn't have to produce new networks. And the nodes and the connections within the network don't have to reproduce either. Their number can just stay exactly the same as the system adapts. What changes is the weighting of the connections, but it's not even clear what it means to talk about those weightings reproducing. So on the face of things, we've got adaptation here without reproduction. And so if this is selection, it's a very non-paradigmatic form of selection. It's a form of selection that doesn't involve reproduction, which is usually thought of as being essential to Darwinian selection. And it looks as though what really is required for adaptation is that a system needs to be reconfigurable in the right way, but it doesn't need to reproduce, and it doesn't need to multiply. I think we can say some similar things about cultural adaptation. So remember, this is the idea that we might well see adaptation in species like ours, and maybe also many animal species, not because of natural selection acting on genetic variation, but instead because of important ways in which members of those species can learn from experience, but also crucially from each other. And this is often framed as a process of selection, albeit one that goes on at the cultural level. So Joe Henrich, in his wonderful work on cultural evolution, says we can survive because across generations the selective processes of cultural evolution have assembled packages of cultural adaptations, including tools and practices and techniques that cannot be devised in a few years, even by a group of highly motivated and cooperative individuals. And there's long been a kind of countercurrent against this approach. So people like Dan Sperber and like-minded colleagues of his have long been sceptical of drawing too close links between the processes that underpin cultural change and at least many aspects of processes of natural selection. And Sperber in particular has been very sceptical of the idea that anything like replication is at work in the cultural realm. Maybe to a somewhat lesser extent sceptical even of the notion of reproduction. But what they've really put weight on is what they see as a really central role of constructive inference, often thinking creatively, the role of constructive inference in cultural transmission. So I'm going to try and just give a quick flavour of what how Sperber thinks about this, and then we'll wrap the talk up. So here's a kind of illustration of what you might think of as the sort of Sperberian kind of worry. So here you imagine we've got a population. I've just arbitrarily split our population into two little groups here. For some reason or another, imagine that boat travel is important to these people, and these five here have hit on a decent way of travelling by boat. They like to use these fairly rudimentary vessels. And this person here surveys all 5 of them, has a look at their slightly different vessels, all nonetheless built according to similar principles, and rather than copying any one of them slavishly, this person instead looks at them, gains inspiration, maybe adds a certain modicum of creative insight, and produces this boat, which let's suppose is an improvement in some way on these. And maybe one of this person's friends does the same. They also look at these boats and they also produce this slightly improved variant, albeit a little bit different to this person's. And you could imagine that, in fact, everyone in this population does the same. Now, note that if that's how innovation works here, then none of these vessels here is strictly speaking having a baby here. No one of them is being copied. Rather, what we have here is a kind of an amalgam, and an amalgam with creative insight added from all 5 of these. And so you could imagine that, in fact, every single one of these people produces a slightly different variant on this improved boat. And then, of course, it could kind of ping-pong back over here. These folk now start looking over here and they notice that they've made various improvements. They start thinking a little bit more. Again, rather than copying any one variant, they take insight from all of them and produce something that is improved once more. Now, of course, this is a massively stylized, highly artificial way of thinking about cultural innovation. But on the face of things could work this way. If they do work that way, is cultural adaptation a result of cultural selection? In a loose sense, yeah, it is. Better ways of building vessels have been retained, repeatedly used as bases for further innovation. But there are big differences between how innovation worked in that stylized example we used and how we think of innovation as usually working in the context of organic natural selection. So at no point did individual vessels have discrete offspring of their own, and the ideas for individual vessels, the plans for individual vessels didn't have discrete offspring of their own either. Rather, innovations were the product of a kind of collective survey of a whole bunch of different individual models, including a certain amount of inference and maybe creative inspiration. So in that sense, there's nothing like a nice, discrete parent-offspring reproductive relationship going on here. For this reason, people like Peter Godfrey Smith, portrayed here on the right, have been skeptical of the idea that we really get simple reproductive relationships going on in culture. So Godfrey Smith says you only get lineages that can be described in terms of reproduction when, as he puts it, the agent supplies simple habits of imitation, picking behavioural models and copying them without transformation and customization of the behaviour required. So not like the example that we just showed. So no reproduction here, but plenty of adaptation. And it looks, though, as though reproduction is not just absent, but reproduction itself is also a really important part of how natural selection goes about explaining adaptation in canonical cases in the organic realm. So in the standard organic case, the way in which selection explains adaptation is via reproduction, because reproduction gives rise to multiplication of the fitter variants in a population, thereby leading to a magnification of the number of promising platforms for further mutation, further beneficial mutation. That form of multiplication is key to, critical to, the way in which selection explains adaptation in the standard organic case. But it's not necessarily present, although sometimes it might be, in the case of cultural adaptation. You don't need to see magnification of numbers of sites for potentially suitable further innovation at all. It's consistent with the case I just sketched that you could just have two individuals just batting increasingly functional variants between the two of them. So I think in some ways Godfrey Smith actually, while getting a lot about this right, I think he overstates the need for cultural adaptation to conform to the standard way in which selection explains adaptation in the biological realm. So he says, In both biology and culture, successive rounds of undirected variation can yield significant design improvements, provided the successful variants in one generation proliferate and provide many independent platforms at which further innovation can occur. It can work that way, but it doesn't need to. You don't need the many independent platforms. It's also possible for that array of platforms to stay highly constrained, as long as we have this form of creative engagement that Sperber thinks is important. And here I should give a debt of thanks to work by Azita Chelapu, particularly in her PhD thesis, Conceptual Challenges in Cultural Selection. Okay, time to conclude. So I've been through these numerous different takes on universal Darwinism. And it seems to me that what survives is a rather weaker, a watered down version, a weaker one that, were you disposed to puns, you might call something like puniversal Darwinism rather than universal Darwinism. So we haven't seen any reason to deny what in some ways is Dawkins's core idea, and is certainly someone like Campbell's core idea, that if systems are going to adapt at all, there needs to be some combination of processes that, on the one hand, introduce variation, while on the other hand, picking the right variants and preserving them. That is what happens in machine learning. That is what happens in cultural adaptation. But when we looked in detail at how those processes work, we did see some really significant differences to those processes and to what you might think of as the canonical way in which selection explains adaptation in the organic realm. So we saw, partly by appealing to machine learning, partly by appealing to cultural evolution, that actually you can get adaptation without anything much like reproduction. You can get adaptation just via a combination of retention and discrimination without any additional explanatory element of proliferation. That's what happens in both the machine learning cases and the cultural evolution case. Or at least sometimes it's what happens in those cases. And we also saw that even when sometimes adaptation does occur through iterated series of cycles of reproduction, Shea's take on machine learning reminds us that there are aspects of adaptiveness that we don't best explain by pointing to features of selective regimes. Instead, we best explain them by pointing to the structure of the adapted system itself, the way in which that system facilitates variation. And these differences, I think, are important. These differences are parts of the central ways in which we go about explaining adaptation. And so, for that reason, yes, if we want to, we can stick with the universal Darwinist intuition that if systems are going to adapt, at some level or another, there has to be a series of processes that introduce variation and others that discriminate and pick the correct ones, pick the right ones. If we want to, we can rest content with that rather weak, rather watered down notion. But if we want to press ahead and produce really scientifically perspicuous explanations, then we need to move beyond that and foreground the differences between these processes of reproduction rather than hide them within just one very generic notion of selection. Thank you.